Look up at the night sky, and almost everything you see, every star, every planet, every wisp of gas, fits into about 5% of the universe. The other 95% is something else. Two substances we have never directly detected, but which together shape the entire cosmos. They are called dark matter and dark energy. For most of the 20th century, astronomers assumed that what we could see was most of what was there. Then, observation by observation, the numbers stopped adding up. Galaxies spun too fast. Light bent too sharply. The expansion of the universe refused to slow down. The simplest explanation, supported by every independent line of evidence, is that we have been looking at a small fraction of the cosmos all along. Over the next few minutes, we will trace the discovery of the missing 95%. We will begin with Vera Rubin and the rotation curves of galaxies, move to the bullet cluster and the cosmic microwave background, examine the candidates physicists are now hunting in underground laboratories, and end with the greatest puzzle of all, the dark energy that is pushing the universe apart. In 1970, the astronomer Vera Rubin, working with Kent Ford, began measuring how stars and gas move inside the nearby Andromeda galaxy. Newtonian gravity makes a clear prediction. Far from the bright center, where most of the visible mass is enclosed, orbital speeds should fall off. They do not. Out to the very edge of the measurable disk, the rotation curve stays flat. Something invisible, with far more mass than the stars themselves, must be holding the galaxy together. Rubin extended this work to dozens of spiral galaxies, and the result was the same every time. The only clean interpretation is that every large galaxy sits inside a roughly spherical halo of unseen matter, with a mass 5 to 10 times that of its stars. No faint stars, no cold gas, no dust can supply this much mass without being seen directly. Astronomers gave the missing substance a name: dark matter. If rotation curves alone left room for doubt, the bullet cluster largely closed it. Two galaxy clusters collided 100 million years ago at thousands of kilometers per second. The hot X-ray gas, which holds most of the ordinary matter, slowed down in the impact, but a map of the total mass, built from gravitational lensing, shows the bulk of each cluster sailed clean through. The invisible mass is collisionless. It behaves exactly like particle dark matter should. The deepest evidence comes from the cosmic microwave background, the relic radiation released about 380,000 years after the Big Bang. The European Space Agency's Planck satellite measured its tiny temperature fluctuations across the entire sky. The pattern of those fluctuations, fit with the standard cosmological model, tells us the universe today is roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. The same numbers reached a dozen different ways. A subtler result seals the case. In the first 3 minutes after the Big Bang, the universe forged the lightest elements, hydrogen, helium, and a trace of lithium. Their observed abundances capped the amount of ordinary matter at about 5% of the cosmic budget. The remaining 27% cannot be atoms of any kind. Dark matter must be something fundamentally new. For 30 years, the leading candidate was a class of particles called WIMPs, weakly interacting massive particles. Many extensions of the standard model of particle physics predict a stable, electrically neutral particle at the electroweak mass scale. A simple thermal calculation then gives the correct cosmic abundance today. This numerical coincidence, discovered in the late 1980s, was called the WIMP Miracle. Direct detection experiments sit deep underground, shielded from cosmic rays, waiting for a rare recall as a dark matter particle strikes an atomic nucleus. The leading efforts, XENO-NNT in Italy and LuxE-PLIN in South Dakota, have pushed their sensitivity by 6 orders of magnitude in a single decade. They have found nothing. The simplest WIMP window is closing. Attention has shifted toward a lighter candidate, the Axion. Originally proposed in 1977 to solve an unrelated problem in nuclear physics, the Axion also happens to be a viable dark matter particle. The Axion Dark Matter E experiment, ADMX, uses a superconducting microwave cavity in a strong magnetic field to convert ambient axions into detectable photons. So far, no confirmed signal. Other candidates remain in play: sterile neutrinos, hypothetical heavier cousins of the known neutrinos. Primordial black holes formed in the first instance of the Big Bang, though most of their mass range has already been ruled out. A small minority of physicists even argue we should modify the laws of gravity themselves rather than invoke invisible matter. None of these alternatives matches the full set of observations as cleanly as particle dark matter. The honest status, as of today, is this: we know dark matter is there, we know it is not made of atoms, we do not yet know what it is made of. The hunt continues with ever more sensitive instruments on every continent and in deep mines beneath them. While dark matter pulls the universe together, something else is pushing it apart. In 1998, two teams studying distant supernovae made a discovery that shocked cosmology. Type Ia supernovae, used as standard candles, appeared systematically dimmer at large distances than any decelerating universe could explain. The expansion of the cosmos was not slowing down, it was speeding up. Saul Perlmutter, Adam Rees, and Brian Schmidt shared the 2011 Nobel Prize in Physics for that result. In the decades since, every independent measurement, the cosmic microwave background, galaxy clustering, gravitational lensing, has confirmed the acceleration. The effect is real, persistent, and difficult to explain. The simplest explanation is a term Albert Einstein added to his equations in 1917 and later called his biggest blunder. The cosmological constant, lambda, is a uniform energy density intrinsic to empty space itself. It exerts a negative pressure that pushes the fabric of the cosmos apart. About 68% of the present-day universe appears to be made of it. But the cosmological constant carries the worst quantitative disagreement in all of physics. Quantum field theory, summing the zero-point energies of all fields up to the Planck scale, predicts a value 120 orders of magnitude larger than the one observed. Either our understanding of empty space is profoundly incomplete, or the dark energy is not a true constant, but something more dynamic. Theorists have explored alternatives: a slowly evolving scalar field called Quintessence, modifications to general relativity on the largest scales. Existing data constrain the equation of state of dark energy to within a few percent of -1, the value predicted by a true cosmological constant. But small deviations remain allowed, and recent results from the Dark Energy Spectroscopic Instrument have hinted, weakly, at exactly such a deviation. Several major experiments will address these questions over the next decade. The Vera Rubin Observatory, beginning its survey in Chile, will track billions of galaxies for weak gravitational lensing. The European Space Agency's Euclid mission, launched in 2023, will map a third of the sky. NASA's Roman Space Telescope will follow. Together, they will measure whether dark energy is truly constant or whether it has been evolving all along. This is a live scientific frontier. We do not know what dark matter is made of. We do not know whether dark energy is a constant or a sign that our theory of gravity is incomplete. We do not know how these questions connect to each other or to the even deeper mystery of why the universe is fine-tuned for structure at all. What we do know, with remarkable precision, is that 95% of the cosmos is something other than what we have spent centuries studying. The story of dark matter and dark energy is the story of how little we still see. Vera Rubin showed us galaxies hide most of their mass. The bullet cluster showed us that mass is collisionless. The cosmic microwave background gave us the numbers. The supernova team showed us the expansion is accelerating, and every experiment built to catch the particles themselves has so far come back empty. The next chapter is being written now by instruments all over the world. If you enjoyed this journey into the missing 95% of the universe, please like and subscribe, and tell us in the comments what cosmic mystery you would like us to explore next.